I'm Peter Braunschweig. I'm a second-year grad student at UCF. I'm one of Theodora's students, and I study exoplanet and brown-dwarf atmospheres.
And I'm Max, and I'm pretty much all the same things as Peter. Theodora, studying exoplanet and brown-dwarf atmospheres. Second-year grad student at UCF. So, does anyone have any questions off the top of their head, or anything in particular from the list behind us that you can hopefully read that and we're not blocking it too badly? Yeah.
I like the second question.
The second question.
Oh yeah, it's already up there. It says, what are the different methods of exoplanet detection and what are the pros and cons of each detection method?
So this was mentioned a little bit in the talk that Theodora gave. So the main two that have had the most detections to date are the transit and the radial velocity method. The transit method, as discussed, was when a planet passes in front of its host star, the light that we get dips, and then later on, actually, we can sometimes, maybe always, at the time I am not 100% certain, but we can also see a dip in the light as the planet passes behind the star. That's because the light that we get from the planet is no longer being reflected towards us, it's actually being blocked by the star, and so that can help people determine that there is in fact a planet there, and size and all the other parameters. And then there's also the radial velocity method, which is where we observe that the stars wobble as the gravity of the planet is affecting the gravitational center of the system, and it pulls it off of the center of the star a little bit, so we can see the colors shifting a little bit as the planets are moving, and we can detect that planets there in that way by the periodicity of the shifting.
And of course, there's also what Theodora was talking about, direct imaging, which is point a telescope at the planet and it actually shows up in the image. And that usually uses something called a coronagraph to block out the light from the star. And it works sort of like if on a sunny day you put your hand up to block the sun so you can actually see. It's like that with your space telescopes. There's astronomy, which works by taking very precise measurements of a star's position in the sky. And so as it wobbles back and forth, that can also be another way to detect there's a planet there. And there's also microlensing, which is when a planet acts as a tiny gravitational lens, so if and its star pass in front of something, you can see the planet signal as well as the star. And so direct imaging is particularly good at finding planets that are not especially close to their stars. Transits and radial velocity, it's much easier to detect things that are close in, because then they'll transit more often or they'll orbit faster, and so the signal will be easier to detect. But a directly imaged planet, it's actually easier to find ones that are farther out. Because if it's closer to the star, then the star's light is harder to filter or block out. And it's also a way to detect systems that aren't seen head-on, radial velocity and transit. Radial velocity works much better if it's close to head-on. Transit almost only works head-on.
And these methods are also a little bit biased towards the larger planets. And you can kind of think that intuitively. The bigger the planet, the easier it is to detect its gravitational influence. The easier it is to see when it's edge on. You can see the dot a lot easier. And the transits, it blocks more of the light, so it's a lot easier to see a deeper, longer dip than a short, but not that long a dip.
I have a follow-up question.
So you said obviously it's easier to see the bigger planets, right? Is there a distribution shape of the planet mass that you guys know of, or?
So, off the top of my head, I forget if there's like a specific name for it, but like, you can definitely see that it's like a little bit more weighted towards those heavier planets. We do see some terrestrial planets, as we know with like the TRAPPIST-1 system first and foremost. But I know that there's the Radius Valley, which is like the observations between like gas giants and like terrestrial exoplanets. There's not many detections there, and it's hard to tell if it's because of like observational bias, like they do exist, or if it's that there's something physical going on that doesn't allow planets in that specific radius to exist. Are there any other questions that are catching people's attention? Any other follow-ups?
I'd like to hear a question regarding the news of life on Venus. Are there any updates on the phosphine gases that you've possibly detected? And to follow up with that, what might life look like on a planet like that? What might life look like underwater or something gaseous?
That's a really good question. Off the top of my head, I don't know about the updates with the Venus.
So I do know that the phosphine detection is very much a subject of debate. There are a lot of people who think it wasn't phosphine, it was something else. I forget exactly what off the top of my head. So it's very inconclusive. It might not have been there at all. The second question about what life on Venus might look like, I think they were proposing that this hypothetical life form would be something almost floating in the atmosphere, like microbes in the clouds. I don't know much more than that, and again, we don't know for sure that phosphine is there. But it is very interesting to think about it.
I'll ask a question. So why haven't we found another planet exactly like Earth yet?
So we have found a lot of Earth mass, Earth sized planets. And I think some of them may even have periods comparable to Earth's orbital period, so years that are roughly 1 year. In terms of telling that it's like specifically Earth-like in terms of atmosphere, having oceans, that kind of thing, we don't necessarily have the data to do that. I don't believe we've actually detected an atmosphere of an Earth-sized terrestrial planet yet. Although I did see a paper recently suggesting that given enough observation time, James Webb could detect one. I don't know whether the amount of observation time proposed is realistic, unfortunately. So we know they're out there somewhere, and as observations improve, we will be able to say, like, there's an atmosphere, here's what's in the atmosphere. And then we might find something very Earth-like and be able to say with confidence that it's Earth-like. We're not quite there yet.
Okay, cool. I have a question. Have we answered the water world question yet about like what life would look like on a water world? Maybe I was in the bathroom.
Yeah, that was like part of a question, but I realized that we actually didn't fully answer that specific part of it. So what it could like look like on a scientific research level, we're not fully sure really. I mean, it's hard to be sure of what life would look like. We only have one data point. I think a lot of like with I'm not sure how to word it, but I mean, it would have to be like, I think there's a thought that it might be closer to like what we think about, like might be around like hydrothermal vents. So that's like at least, I think it's like Enceladus. I could be wrong, but that's like where we think other life in the solar system might be. And since it's such a like water-heavy place, I think that it's possible that life that formed there formed around like hydrothermal vents. So we might lean more towards like the microbes and like the small single-celled organisms that evolved first of all to settle down and look like that.
Yeah, there's like salts and all that. Like coming out of like the vents on inside, things like that. That's cool. Cool. Sheep and roast like
So for Enceladus specifically, I know there have been proposals to send another spacecraft there, fly through the dunes. We know there are organic molecules in the dunes. We don't know if those are coming from life or not. They might just be left over from the solar system formation and what went into Enceladus' core. So for Enceladus specifically, we might be able to send a spacecraft there and look. For a water world exoplanet like Enceladus with an ice shell, we might never be able to tell. For a water world exoplanet that doesn't have an ice shell, then maybe it would have an impact on the atmosphere that we could detect. Looking for molecules that wouldn't ordinarily show up in the same place. Like, if you're looking at Earth, the amount of methane and the amount of oxygen would not normally both exist at the same time. All of the methane should react with the oxygen and go away. So that's something like that on another planet would be a potential sign of life, and that might happen even on a water world if there was, for example, photosynthetic algae.
Do we have any other questions? All right, I think that's it.
Oh, all right. So thanks everyone for coming to our second Astronomy on Tap. We'll be doing this every month until question mark. At least June, yeah. We might take a break in the summer, who knows, maybe we won't. But if you're interested in giving a talk on one of these things, feel free to sign up, contact one of us, let us know. And again, if you have any suggestions for how we ran things, that thing sounded really weird. Please fill out the form. Let us know how you would change things if you could. And yeah, I think that's it. So thanks everyone again for coming out tonight. Thank you, Theodora. Thank you to Max and Hugh, our panelists. And we hope to see you again next month on the third Tuesday of the month. I think that's January 17th. Cool. Who knows what we'll be talking about yet? We'll figure it out by the time we get there.